in putting together proofs of rules of inference, we need justifications for the lines that we write. You can refer to other rules of inference, you can state givens, you can introduce tautologies. But now we're going to introduce a new justification that's perhaps the most powerful, but almost certainly the most often misused. That is an assertion. At any point in a proof, you can write any statement you want, as long as you justify it as an assertion. An assertion, however, is not yet proved. You're merely announcing, I claim this is true, but I have not yet shown it. So an assertion has to be subsequently proved, and you are absolutely not allowed to refer to that line until it has been shown. Because for now, it's merely a claim that is not known to be true, so you'd better not use it as a reference to anything else. The way you indicate that you haven't proved this yet is you immediately begin subnumbering. What this means is perhaps in line 8 you made an assertion. Then the next thing you write is line 8.1. I also like to indent the line 8.1 to make it even more clear that what's happening is subservient to the assertion in line 8. We've essentially created a new problem for ourselves. Let's justify line 8. So we began in line 8.1. Next would be line 8.2 and so forth. Until you have completed the proof of line 8, which depends on the style of proof, and we haven't gotten to that yet, but until line 8 has been proved, you cannot refer to it because it's unproven. One of the most common errors students make is they refer to line 8 in the subnumbering 8 point whatever, which are lines that are supposed to be justifying why line 8 is true. You cannot use a line to justify itself. So for example, you might assert in line 8, P implies Q or not R. Then in line 8.1, you would have to begin justifying that, and that would continue with line 8.2 and so forth until that proof of the assertion was complete. And what's critically important is any line numbered 8 point something cannot refer to line 8, because anything numbered 8 point something is subservient to the assertion of line 8 that hasn't been proven yet. All right, so we can make assertions, but then we have to justify them. Different styles of assertion have their own styles of justification. Okay, we haven't really gotten into the details yet. But once the assertion is fully justified, let's suppose for the sake of argument in line 8.5, all of those subnumbered lines, put a box around them and cross them out, and now cross out the word assertion, because you have completed according to whatever style there is, which we haven't really fully discussed. But once you complete that proof, now line 8 is justified. However, everything that you did in 8.1 through 8 point whatever is no longer accessible. All of those lines, 8.1 through whenever that was completed, are part of the proof of line 8. Now that line 8 is proved, you cannot refer back to those lines. This will make more sense once we get into the details of how these things are proved. So for example, in line 8, we might assert this statement. Now we have to begin justifying it, which will depend on what style we use. Stuff happens until something concludes the style. Now, 8.1 through 8.5 should be crossed out because the justification of line 8 is complete. This is now no longer an assertion, so you cross that out. You can now refer to line 8, but you move on to line 9. All of these lines are now essentially gone. This is like saying, I claim this is true. Here's why this is true. Now that we've proven this is true, we can go back and continue where we left off. So after line 8 comes line 9. And now that line 8 has been proved, you are allowed to refer to it. You are not allowed to refer to this anymore, and we'll see why that's very important. Okay, and that's what that box is supposed to remind you of. The box around 8.1 through whenever that is concluded shows you that you're no longer allowed to refer to these. They were entirely part of backing up the justification of line 8, and once that's done, they're off limits. So, in summary, once you assert something, you have to immediately begin to justify it. Once you justify that assertion, all the work that did so is now off limits for the rest of the proof. So when we make assertions, we have to justify them, but what methods are we permitted? If you happen to assert a conditional statement, one method is known as direct proof. Now you've asserted a conditional statement. If the hypothesis is false, then the conditional statement is vacuously true. The only possible way a conditional statement could fail is what if the hypothesis is true? So if you assert a conditional statement, the first thing you do is you move on and you say, let's assume the hypothesis is true, justified as an assumption for a direct proof, and we abbreviate that as assumption direct proof. You have asserted a conditional statement. If the hypothesis is false, there's no issue, it's vacuously true. So you assume the hypothesis is true. Then what you need to do is use allowable techniques to derive the conclusion. If you have shown that by assuming the hypothesis is true, the conclusion has to be true, then you have shown that your conditional statement that you asserted is correct. If the hypothesis were false, no issue, vacuously true. Assuming the hypothesis is true, conclusion has to follow, therefore conditional statement is still true. And that concludes the proof of the assertion. Okay, so let's see how this works in the following rule of inference known as transitivity. Well, we start with our two givens. P implies Q, Q implies R, there's our givens. Now the proof will be complete if we can make this line show up. But for now, it's just an assertion. I have no reason to believe it's true, but I know I want it to be true. If I can back this up, then we'll be done. Now we asserted a conditional statement. So I have to move on to line 3.1 and somehow justify it. Since I asserted a conditional statement, I'm going to do a direct proof and assume that the hypothesis P is true. Now I have P that I can refer to. I still cannot refer to line 3. Line 3 has not been shown, but lines 1 and 2 were just givens. I can use them. So if I have P, I can use modus ponens and extract Q. Now that I have Q, I can combine it with line 2 and use modus ponens again and extract R. So by assuming P was true, I was able to show that R must be true. From the hypothesis P, I got to the conclusion R. So starting from the hypothesis, assumption for a direct proof, I used allowable techniques and I got the conclusion. So I put a box around it and I say this has been concluded. That is a direct proof. By assuming the hypothesis, in this case P, I was able to work towards the conclusion, in this case R. Now that this line is no longer an assertion, we're done. It can be used because the assertion has been justified, and now I have made the desired conclusion appear as a justified line, so we've completed the proof. Now that we have completed a proof of this rule of inference, we can use it in the future, and this is called transitivity. It has two givens. They are both conditional statements. The conclusion of one of them is the hypothesis of the other, and the thing you extract is a conditional statement that cuts out the middleman. If P leads to Q and Q leads to R, then P overall leads to R. And that's transitivity. And we can use that as a rule of inference from now on. So let's try to put together a two-column proof of the following rule of inference. Now what we could do if you absolutely hate two-column proofs is you can do this as a truth table. One given and a second given implies the conclusion. First given and second given implies conclusion. If you can construct a truth table for this and show it's a tautology, you are done. That is a perfectly legitimate proof. But it's got 4 literals, A, B, C, and D, so it needs 2 to the 4th or 16 different rows. You'd have to negate C, then make this conjunction, then make this conditional statement. Negate A, make this conditional statement, then conjoin those two. Negate B, make that conditional statement, and then finally make this one. 16 rows with 8 or so intermediate steps. While doable, it's extremely tedious and rather long. Instead, let's just do it as a two-column proof. So I begin by stating my givens, and there's 2 of them. So I have A implies not C and D, given. The negation of A implies B, that's also a given. All right. Now somehow I want to combine these things together. And it might not be obvious how I do it, but I know that if I can make the negation of B implies D shows up, I'll be done. But I can't figure out exactly how to do that, so I'm just going to say that's my assertion. If I can justify this assertion, we're done. Now we did assert something, so we have to immediately move to a subnumber. And so far, the only technique we know of for backing up assertions is a direct proof. Now, a direct proof can only be employed if you asserted a conditional statement, and thankfully we did. And a direct proof says, take the hypothesis and introduce it into the mix, backed up as an assumption for a direct proof. The goal now, having assumed the hypothesis, is to do allowable steps and get to the conclusion D. Well, now that I have the negation of B, I can combine it with the given in line 2 via modus tollens. If I do modus tollens with lines 3.1 and 2, then I can say, since I don't have this conclusion, I must not have had this hypothesis, and the negation of this hypothesis through a hidden use of double negation is just A. Well, now that I've got A, I can apply modus ponens with what I just extracted in line 1. So in line 3, I can say, all right, I combine this hypothesis, I feed it into this conditional statement, and I get out that conclusion there, the negation of C and D. Now remember, we're working on the justification of this assertion. We started with its hypothesis, negation B. If I can just make D appear, then we are done. And we can, if I specialize this conjunction, we can jump right ahead and say, since I had not C and D, by specialization on line 3.3, I can extract the single literal D, and that's line 3.4. And now, having moved from the assumption of the hypothesis, we have derived the conclusion. So this is no longer an assertion, and now that this is no longer an assertion, we have fully completed the proof. This is not the only way we could have done this proof, okay? So for the sake of completeness, let's actually do this entire thing again. Pause here to look over this one again if you like, because I'm about to erase everything. Well, it's going to start very similarly. I mean, stating our two givens, there's not a whole lot to be said there. That's a D. This is a given. And the negation of A implies B. That is our conclusion. Sorry, given. All right. Here's a hint. I want to apply transitivity. Remember, transitivity says if you have two conditional statements, the conclusion of one is the hypothesis of the other, you can cut out the middleman. I don't have that. I do have two conditional statements that seem to involve A, but the hypothesis here is the negation of this hypothesis, so I can't just use transitivity, but what I can do is I can talk about the contraposition. What is the contrapositive of line 2? Remember, the contrapositive of a conditional statement says a conditional statement is equivalent to reversing the hypothesis and the conclusion and negating them both. So instead of not A implies B, this becomes not B implies A through a hidden use of double negation instead of writing not A. Now I can use transitivity referring to lines 1 and 3. We have two conditional statements. The conclusion of this one is A. The hypothesis of this one is A. So transitivity will allow me to say that not B will go all the way to not C and D. I can now apply a distributive property to this line. Negation, if something implies a conjunction, in other words, not B implies this conjoined not C and D, well then, not B will imply not C, but also not B will imply D. Now I can simply specialize this and extract its second argument, the negation of B implies D, which is exactly what we wanted. So we were able to construct a proof where we simply asserted this and did a direct proof, assume the hypothesis and work towards the conclusion. But we were also able to do a proof without the assertion. Neither one of them is more or less correct than the other. These were both totally legitimate proofs, even though they looked fairly different. In fact, there are even more ways we could prove this. Never think that there is only one way to do a problem. If you can come up with a way which is correct, that's great. Let's talk about some errors that students make a lot when it comes to direct proofs. So here's a rule of inference which is totally not valid. Just because you have P does not mean that P implies Q. However, here is a proof that you might see someone hand in. So if I receive this as an assignment, let's just check. P given, absolutely, that's fine. P implies Q, that's what they're trying to show, so they've asserted it. Great. What they have to do now is begin from the hypothesis, so they've assumed P. Now they need to work towards the conclusion Q, which they say they achieve by applying modus ponens to lines 2 and 2.1. Well, 2 is P implies Q, 2.1 is P, and if I combine these with modus ponens, I feed in the hypothesis and I get out the conclusion. But what's the error here? The error is that in line 2.2, they have referred back to line 2. 2 point anything is part of the justification of why line 2 is true. What they've essentially done is said, I claim line 2 is true. The reason why are the following arguments, which already assumed that line 2 was a valid thing that we could refer to. This is what's called the circular argument. They have justified line 2 by referring to the truth of line 2. That's not legitimate. So once you assert something, the subnumbering is supposed to really help you not do this. 2.2 cannot refer to line 2. Okay, similarly, the line 4.8 cannot refer to line 4. The line 12.4 cannot refer to line 12. You can even have subnumbers within subnumbers. The line 12.1.6 cannot refer to line 12.1, and it also can't refer to line 12. If you had the line 4.3.2.8 because you made an assertion within an assertion within an assertion, which is a totally allowable thing, okay, we'll actually see some examples of it. This last subnumber says I'm still working on the proof of 4.3.2, but since 4.3.2 is involved, I'm still working on the proof of 4.3. Since 4.3 is involved, I'm still working on the proof of 4. So at this point, you cannot refer to line 4 or 4.3 or 4.3.2. So subnumbering really tells you what you are or are not allowed to refer to. Okay, notation can really make stuff easier and help you avoid errors. Here's another common mistake. Okay, so here is another rule of inference that is not valid, but here's a possible proof of it. So take a look at this and try to see what mistake was made. Well, we've stated a given, we've stated a given, we've stated a given, that's fine. We've made an assertion. Now, it's not the thing we were after, but that's fine. Remember, you're allowed to assert anything you want. I assume the hypothesis line P, okay. Modus ponens between this line, 4.1, and line 1, correct. Modus ponens between line 2 and line 4.2, correct. I didn't refer back to line 4, so there's not an error here. Okay, so now line 4 is justified, that's great. Line 5 says, apply modus ponens to line 3 and line 4.2. If I have S and S implies R, can I get out R? So what's the mistake? It has to do with that subnumbering system. This all began by assuming P is true. When P is true, S is true. But in our original formulation, we don't really know if P is true or false. This was an assumption made as part of a direct proof. So everything that comes after it in these subnumbers is based on the assumption that P was true, even though you don't really know that. This is why we box this off and say, okay, once you go from this assumption to this conclusion, everything in this box is tainted by the fact that we assumed P is true, and that might not be the case. So everything in this subnumbering system should not be referred to once you have finished backing up line 4. Using the assumption of the hypothesis to derive the conclusion is how direct proof works. But once you've completed that, you use this box to say, now I can't use any of this again, because this line, S, was based off of the assumption we made in line 4.1, which might not be true. So I shouldn't really be using it once I get past proving line 4. Okay, so once you have completed a subnumbering section, never refer to those subnumbers again. This was all in service of showing 4 was true. Now I can refer to line 4, but I cannot refer to these anymore. It's worth pointing out, by the way, that from line 1 and line 2, P implies S, S implies Q. Transitivity could have gotten you right here. And if we remembered transitivity was a thing, well then we wouldn't have had these around and we wouldn't have been tempted to use them. Okay. But this is not a valid rule of inference anyway, so there was no correct proof we could have come up with.